Okay, so for question number 1, we need to know the definition of an electrolyte. So essentially it's any compound that breaks into a cation and an anion. And then we need to know strong versus weak. So the strong are going to be your salts, strong acids, and bases. So if you don't remember those, I would brush up on them. And then everything else is going to be a weak electrolyte or it's going to be a non-electrolyte. So for the first one, we know that HCl is a strong acid, right? So therefore, this should be a strong electrolyte. For potassium nitrate, that's a salt. So that is also going to be a strong electrolyte. Sorry about my handwriting. Glucose does not break up into a cation and an anion, so this is going to be a non-electrolyte. And ammonia is going to be a weak electrolyte. And that's it for the first question. So that was all basically definitional. So now for number 2, we need to find moles of solute particles. That's the key word here. And 1 liter is also the key word. So remember, molarity is in moles per liter, meaning that we can multiply this by our 1 liter, right? And that will just give us moles. But then we need to convert that to moles of solute particles. So here we'll start off with 0.3 molar. We're going to times it by 1 liter. You don't really need to do this step, but just to make sure that we have this in moles. So we have 0.3 moles, and then we need to figure out what ions are in solution. So in this solution we have potassium plus and bromine minus, right? So when you dissolve this in water, that is the cation and the anion. So we have 1 of each. So all we need to do is multiply 1 times 0.3 plus 1 times 0.3. And the 1 is accounting for the first potassium and the other one is for the bromine. And this should give you 0.6 moles of solute particles. Okay, and it's the same idea for the next one. So when this breaks up into solution, we have H plus and NO3 minus, so that's our cation and our anion. And so we do the same thing here. We're going to do 0.65 molar times 1 liter to get that into 0.065 moles. Now we're going to do the same thing where we multiply 1 times 0.065 plus 1 times 0.065. Again, this is accounting for the H plus, and this one over here is for the NO3 minus, and this should give you 0.13 moles. So pretty simple, right? Okay, the next one, not the same as the first two because those were a 1-to-1 ratio, right? So here we have barium 2 plus. So to counteract the 2 plus, we need 2 of the hydroxides. So we have 2 OH minuses, right? So now we need to account for this 2 here, but again, it's the same process. So we'll go 0.004 molar to 0.004 moles. And now we're going to do 1, because we have 1 barium 2 plus, times 0.004 plus 2, since we have 2 OH minuses, 0.004, and that should give you 0.012 moles. Okay, and then for the last one, ethanol, this is not going to form a cation and an anion, right? So we don't need to do what we did previously. All we need to do is do 0.06 moles per liter, right? Times 1 liter, those cancels out, and then we just get 0.06 moles of ethanol. Pretty simple, right? Okay. The next question is basically critical thinking. So when a compound is dissolved in water and the resulting solution conducts electricity, we can conclude that, well, if something's conducting electricity, right, it's probably an electrolyte, right? They didn't really give us much more information. So the only two that apply are 1 and 2, because we know it's an electrolyte since it's conducting activity, so we can get rid of option 3. We can't really tell if it's strong or weak because they didn't give us enough information. Okay. Draw several water molecules around the pair of molecules below, indicate what type of interactions each water molecule has with the molecule it is next to. Okay, so we need to draw some hydrogen bonding with water, right? So I'm going to start on the left molecule. So this oxygen right here can hydrogen bond with a water that's over here. And then this hydrogen that's on this group can interact with an oxygen on a nearby water like that. And that's as many interactions you're going to get on that molecule. On this one, this might take me a little bit to draw, but it's the same idea. Your hydrogens on the molecule are going to interact with the oxygens on nearby waters, and your oxygen on the molecule is going to interact with hydrogens on nearby waters. So ideally there should be 2 waters per each of these. Ooh, I don't know where I'm going to draw this one. I didn't give myself enough room. That. Like that. And then we have the hydrogen and the oxygen. Alright, so lots of hydrogen bonding to oxygen, right? Hopefully you can read that. So based on the pictures you drew, which molecule would be more soluble in water and why? So essentially the more soluble one is going to be the one with more hydrogen bonds. So that would be the one on the right. So more hydrogen bonding ability, because let's just say it's not actually going to bond all of those waters, but it will interact. All right. So draw a carboxylic acid with the structure CH3COOH. So what's nice about when they give it to you like this, it's usually telling you the order of the atoms. So I'm just going to start with CH3. Just going to draw it like that. And then the next thing, right, is a C, carbon. The next thing is 2 oxygens. And then a hydrogen, right? So looking at this, that carbon only has 3 bonds, and carbon always wants 4 bonds. So this should be a double bond to that oxygen there. And this is the structure of carboxylic acid. Not the most beautiful thing in the world. Okay, so draw the anion that is formed when the acid loses a proton, and then draw the resonance structure. So that means that we are going to be losing this proton right there. So essentially, the only thing that's going to change is the right side. So our CH3 is going to stay exactly the same. And then we are going to have our anion, right? So something needs to be negative. There you go. And then the resonance structure of this is just, remember, you can move that double bond to the other oxygen and make the other oxygen a single bond. So your CH3 stays the same. We'll make this one a single bond with a negative charge, and we'll make this other one a double bond to the oxygen. And that's it. All right, on to number 6. So we have a beautiful picture here, and we're looking at magnesium chloride, so let's just write it out first. Magnesium has a 2+ charge, meaning that we need to counterbalance that with 2 chlorine 1 minuses. So when looking at these solutions, we know that we have twice as many chlorines as we do magnesium. So which one of these pictures has almost twice as many chlorines and magnesiums? So obviously not this one, right? That one has way too many magnesiums. This one, they're bonded to each other, which is not what happens in solution, right? They break up into magnesium 2+ and Cl-. So you should have gotten A. And I believe if we count here, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 chlorines to 4 magnesiums. So that works out nicely. So you should have gotten A for A. So what is the amount represented by each large sphere? So this is similar to what we did all the way up here, but we're just going to add one more little factor. Okay, so they gave us, what, 0.952 grams of MgCl2, right? So we want to get rid of grams and go to moles, right? So we're going to multiply this by something that's in grams on the bottom to cancel it out, and then moles, right? So we're going to do this by the molecular weight of magnesium chloride, which should be 95.2. So now our grams cancel out, and we are in moles. Yay. So this gives us 0.01 moles. And we're doing this for chlorine, and we know that there's 2, so remember from the previous problems, we have to multiply by how many ions are in the solution. So we're going to multiply this by 2 chlorines, and that should give us 0.02. And it would be nice to end here, right? But they said what's represented by each large sphere. So now we need to divide this number by how many large spheres we have. So we have, I believe I said it was 8 spheres. And that way we can get it of moles per each sphere. Oops. And that should equal 0.0025 moles per sphere. So that is how, ooh, why is it moving? That is how you do that one. All right, moving on to the last one, calculate the molarity of NH3 in an 8% mass, and then they gave us the density. So what we can do here is we want molarity, right? So we want moles per liter, right? Meaning we need to find moles of this thing and we need to find liters of this thing. So I'm going to start by finding the liters of this. Since they gave us the density, we can easily figure that out. So we're just going to say this is a 100% solution, so 100 grams. So we're going to do, this is calculating our milliliters here. 100 grams of solution divided by the density that they gave us. So 0.9651 grams per milliliter. So that will cancel out the grams and that will give us milliliters. It should be 103.616 milliliters. And then obviously we can convert that to liters easily. So let's just go ahead and do that. Just move the decimal over 3 places, right? 0.103616 liters. All right, so we solved the denominator. So now we need to find moles. So what we have to do is do 8% of 100, which is just 8, right? 8 grams for NH3, right? All right, so we're in grams and we need to get to moles. We know how to do that, right? We use the molecular weight of the NH3. So remember, we want to have grams on the bottom and moles on top, so that way we can cancel out the grams. So the molecular weight is 17.031. Your grams should cancel out, and that should leave us with moles. 0.469 moles of NH3. Sorry, that's a little sloppy. All right, so we got liters, now we got moles, and all you have to do is put them together. So I'm just going to write this down one more time, moles per liter. You can solve for moles first, you can solve for liters first, it doesn't really matter. So now we're just going to take the numbers that we calculated and divide them. 0.469 moles divided by 0.103616 liters, and that should give you 4.53 molar. And I believe that is all the questions.